Good afternoon to all. My name is Gabriele Centi from the University of Messina. I co-chair this session on after treatment together with Chris Marshall. And it's time now to start with the lecture. This is keynote lecture of Professor Fabio Ribeiro from Padua University, an overview of ammonia SCR on copper-supported Zeolites. Please.
Okay, good afternoon, everyone. I would like to start by, I was just asked why you have so many co-authors on that paper. and the answer is that I wish I could do all this work myself, but I can't. So this is one of the, at least in the US, one of the modes of the government wants to push, bring people together so that I wouldn't be able to do that really without this team. So people with different expertise. Nick worked on the kinetics. Bill works on the theory. Jeff Miller works on many things, but mostly here the X-ray absorption. Alex keeps us honest because he knows how those things are used, and it's great to have somebody like that. So that the work hopefully is relevant, and of course the people that really do the work. In fact, all of them presented their work already. So I guess that my mission here is to summarize what they've done. So they had time to go into much more detail than I can go here. So the reaction selective catalytic reduction, here you have an overall reaction of what it is. There is one that's called standard that you use a NO, one that's called fast that you use an equimolar mixture of NO and NO2. And here is an example, thanks to Johnson Matthey, of how this looks like in practice. In fact, they have this exact piece in real size, and if you're nice to them, like Les, you can borrow. They let us borrow this, so on our NSF sponsored projects, we can actually show this. You should ask them. It looks really beautiful, a big piece of this catalyst. So the reaction SCR happens on zeolites and on many zeolites, and so there's no problem carrying out this reaction. They work well, high rates, and everything is fine. But the problem is that in practice, you need to regenerate those materials every so often, and the conditions are very high temperature, a lot of steam, and most zeolites just fall apart, except for this zeolite called the chabazite, that has this amazing property that even if you steam it at 900 degrees C overnight, you come back next day, you measure the catalytic performance is unchanged. So it's an amazing material. Why is that? I'm not going to talk about this. Maybe if you ask Raul Lobo, maybe you know, tell you why is that such a nice material. But here is a picture of what the zeolite has 8, 6, and 4 rings. And here you have a picture of a copper, gray, oxygen, red, silicon, and aluminum sides, and then you see a copper there. So what we'd like to do is find out on the active catalyst what is the active site, what form of copper it is, what is this species under reaction conditions, we would like to know, and what's the state of copper. So it's, of course we don't know all the pieces about it, but we know hopefully a few pieces of what's going on this chemistry. So I will start with NO oxidation and SCR kinetics on the chabazite catalyst. So I will start with a discussion with you about NO oxidation. So the objective of the NO oxidation is not as it relates to SCR, but it's just as a characterization tool. So keep this in mind. In fact, when we do this NO oxidation characterization, there's no water. It's just NO, oxygen, NO2. And so we are using that as a probe to identify what copper configurations catalyze this particular reaction. So the samples that we're going to going to use. We prepared those ourselves. We had to. We can't get those commercially. So Rahul Lobo again was the one that told us how to prepare those samples and how to characterize them to make sure that we have the correct material. They are most of those are different batches. The small changes you see, and we've done a liquid exchange of copper. Here's the copper weight. Maybe you're more interested on the copper to alumina ratio. So you could get theoretically to a maximum of 0.5 if you go copper 2. So this is, we have a range of catalysts from the pure zeolites to 0.35. So we've done the kinetics on that. I'm not going to show you much on the detailed kinetics. Those were covered in other talks, but for the NO oxidation, we use NO and we make sure that we add the product too, because it inhibits very much the rate, the reactors. If you add NO2, they become differential. And then we measure the apparent activation energy and the apparent orders of for this reaction. I will show you some activation energies and some reaction orders. So here is one example of the dependence of rates with temperature and Arrhenius plot, and from that we can derive apparent activation energy. So so here the first results. What happens if you the series of 7 catalysts that I showed to you? What happens when you change the copper to alumina ratio and measure the NO oxidation rate per total mole of copper? We were surprised to find out that nothing happens with the first samples, and then all of a sudden the rate of oxidation goes up. So we're wondering what's going on here, and in particular if those catalysts here would then be active for SCR. So then the answer is here. If you do now the SCR rate at those conditions, now we have water and CO2 as a function of the copper to alumina ratio, you can see that as you add more and more copper, the rate goes up linearly, which means what you're doing there is you're just adding more and more sites, and then eventually they saturate, and you see, you can put a line here about 0.2. You see a lot of this copper alumina ratio 0.2. What happens there? So if you heard the other talks, you know what's going to happen here. Why is that there is this number is around 0.2 is quite important. But the conclusion here is that the SCR rate goes up linearly. So you're just filling size, they're all the same, and then they plateau, and the opposite happens with NO oxidation. There is no rate on those samples, and then here, then you start seeing rate going up. So we've done some characterization on those catalysts. This particular one, we just take the samples in air. There is not in situ or operando. It's just the sample in air, and we've done some UV vis. So it turns out that if you have if the copper would be in this hexa-aquo type of configuration, there is a transition, an electronic transition that happens at about 12,500 wave numbers. And then with UV vis, you can find out this transition. So if you take this series of catalysts, this is the transition that I'm talking about. Those are related to complicated type of transitions. We're not using those. We're using this particular one. And so what you see is that as the for these different samples, you can see that this peak is going up. So it looks like that this is the as I mentioned to you, this is this particular transition here is this transition for this particular compound. So if this is actually the compound that you have on samples that's just in air hydrated, another way you can look at them is by X-ray absorption spectroscopy. So here is actually the sample in air on red one. Let's take this. This is just the aqueous compound. This is not a catalyst. You just put this in solution, and you took the zanes, and then this one here on the zeolite, you get exactly the same sample. You may say, well, I don't know, I haven't seen the other standards. If you have other standards, they're quite different. So this is really a way of showing that this is this compound is probably in presence, and what's happening there then, if you have your zeolite, if you just leave it in air, it hydrates enough that the copper swims on the zeolite gauges, and it looks like to the copper itself that it is in solution. So it's completely hydrated. This is not under reaction condition. This is in air. So here is if you plot the intensity of this peak that I told you as a function of the copper to aluminum ratio, and that's the points to here. You can see things go up. And now better yet, if you make a plot. If you plot the SCR rate as a function of this UV intensity transition, there is a linear relationship between them. So that means then these isolated copper 2 atoms that you can see on UV vis, they are probably the precursors of the active site. So that's what this data is telling us. So then, of course, what I'm going to talk to you in the rest of the talk. If this is at ambient conditions, what happens when this thing goes to reaction conditions? It turns out that you lose some of those water, then the copper and binds with the zeolite, and you start seeing copper-oxygen silicon type of bonds. And then this is the state under SCR conditions. We'll talk about that. So just to remind you, this is the NO oxidation rate in red, and this is what you see on these DD transitions. On the case of, if you're looking at NO oxidation, there's no correlation between one or the other. So this transition here is specifically for these copper 2 ions, and if you have them, there is no rate for NO oxidation. So then what's the configuration that catalyzes NO oxidation? So I showed to you what catalyzes SCR. So here is we use a technique of X-ray absorption spectroscopy. So this is we have you can use either the Zane's region, X-ray absorption edge. In particular for copper, there is a transition, electronic transition that occurs in this region. So it's very easy to see if you have a oxidized copper. Watch the oxidation state, and then on the x-axis range. Then if you heard Jeff Miller's talk in the morning, then you can have information about long-range structures. What happens with your copper? So with the combination of this structure, you can look at what's going on the catalyst. So here is again the 7 samples that I showed to you, different copper to aluminum ratio, and then what we are doing here by looking at the shape of the zanes and the standards that we have, which is the isolated copper, and a standard that we have copper oxygen. It's that you have copper oxygen bonds. You can see when you increase the copper oxygen character, then there is a shift from the standards that you can see, and then you can do a linear combination of the zanes, and you can find out how much you have copper isolated or how much copper oxygen bonds you have. So you can see copper, oxygen, copper. You don't know how far that goes, but that you know that copper is not isolated anymore. There's an oxygen bond now. So then if you plot now the NO oxidation rate as a function of this copper that we call copper X or Y, which is those bonds that the x-axis can see, you see that there is a correlation. All the samples that had no NO oxidation would be here, and those are the samples where we saw NO oxidation rate. And again, there is a correlation between what we see with x-axis and the NO oxidation rate. So then, to understand this, then the theory becomes very important. And of course, I'm not going to go into details, but Bill Schneider has been calculating some possibilities of what's going on. What is this copper entity that can do NO oxidation. And so here is some ideas, and you have to see stability. So we think that we can probably form copper dimers. And then there are different types with, of course, different energies. But we can also say, if you try to look at NO oxidation on isolated copper pairs, so you see that this is just the energy of the various intermediates, and versus the one that you have a copper dimer in an 8-member ring cage. So it's probably, at least it's feasible that you have a mechanism where we go this way. The barriers are not that high as opposed to the one that would see copper 2 ions, which is what we see in practice. We don't see that happening. We see those. So just to summarize it to you, what I told you about NO oxidation. So NO oxidation in this case is used as a characterization tool. It's not done under SCR conditions. I cannot measure the rate of NO oxidation under SCR. I don't know if NO goes to NO2, that goes to then some other reaction under SCR. That's not what we measure. We just measure NO oxidation by itself versus standard SCR at similar rates, at similar concentration. So you see that there's a vast difference. So if the mechanism, always saying that if you're trying to study NO oxidation separately, they will not correlate with if there is NO oxidation under SCR, because the rate of SCR is much, much higher. So you can't have a sequential reactor where you do NO oxidation first. At least the mechanism would be quite different. So then the question is, where does this copper to alumina ratio equal to 0.2 comes from? So if the issue here is that when you add the aluminum, the silica to alumina ratio is about 4.5. When you add the aluminum into the zeolite gauge, you think that the aluminum is going to be randomly distributed. So if you want to stabilize copper 2, you need to have 2 aluminums. But if the aluminums are too far apart, you can't stabilize copper. If they are too close, you can't stabilize either. You have to have them at the right distance. So from previous work, it looks like that this distance is about 5.5 angstroms. So then now if you have this constraint, if you know your silica to alumina ratio, if you want to find out what's the probability of finding 2 aluminum-aluminum pairs that are on the same distance, that's the number I would like to see, to find out how much of copper we can exchange with this zeolite. So here's the work of Chris and Hugh Schneider. Here you can see the silica to alumina ratio as a function of the maximum isolated copper to aluminum pairs. So we have about a silica to aluminum ratio of about 4.5. So in this graph you see 5. And then the maximum isolated copper to aluminum would be 0.24. We have experimentally defined that 0.2 is around the range where we see at that transition. So this tells us that this model tells us that it's this model is would be a possibility. So then that's where that 0.2 number comes from. So in the first part of this talk, so the NO oxidation does not proceed on isolated copper 2 ions. The isolated copper 2 ions, we think are the active sites for standard SCR. And I mentioned to you the NO oxidation performance. We do that separately, cannot correlate with SCR performance. Those are quite different. We think that the NO oxidation is favored on this copper oxide type of species. We think that probably those are dimers that are inside the zeolite gauges. So first, if you put copper in, you first populate the zeolite with those isolated. When you have enough of them, you start forming dimers, and that's where the NO oxidation comes up. And the number 0.2, I explained to you that those are from the aluminum-aluminum pairing at the right distance. So then the next question is to do now an operando actually absorption study on those samples. We want to find out what's the active state of copper under reaction conditions. So I told you that it correlates with the number. I told you the number is copper 2, that's exchanging the zeolites. Those are the sites for SCR. But what is the state under reaction conditions? So to run those experiments, here you can see a picture of the, it's called the insertion device number 10 at the Argonne National Lab. Here we can bring all our equipment on a chart. So here is the IR analyzer, temperature controllers, and here you can see the cell, the X-ray beam passes through the cell at the same time that we are carrying out the reaction. We call it operando not because we want to make it a fancy name, but we want to distinguish this from in situ. So operando means that at the same time that you're measuring the X-ray absorption, the Zanes, you're measuring the rate at the same time. So there's no question that you know that catalyst is doing exactly what you want. You know what the concentrations are. If you are in the differential conditions, you know what the state of the catalyst is. So you can really correlate one with the other, as opposed to an in situ technique. An in situ technique for this reaction, what would mean is that you can press a pellet and put on the reactor and you can flow your gases, but the gases don't really go through the catalyst. So this reaction, it's very fast reaction. It doesn't go to equilibrium. So if you do that, just an in situ experiment with a pellet, you have a very high risk, and probably that's what's going to happen. That close to the catalyst, the concentration is completely different than what your gas phase is. And as I'm going to show to you, the state of the catalyst is very dependent on the concentration of the gases. So you can't really do this type of experiment unless you spend the time to do a real packed bed reactor. So this is made out of carbon. So the gases go here about half a liter per minute. And as I mentioned to you, you measure the rate at the same time. This is how the reactor looks like closed. Those experiments, you really need an expert like Jeff Miller with you, because to get really good data, an expert is needed. Although the setup is not complicated. In fact, if you go to our previous papers, you can build a cell like this very, very easily. So here's an example of what happens under operando condition versus in situ. Here's the same catalyst under the same conditions, almost a little bit different, but you can, this little blink that you see there is the oxidation of copper. So if you do the same reaction, same catalyst, but one is in situ versus operando, one is more oxidized than the other. You don't know why. It's the same catalyst. The problem is that what you think that the catalyst is saying is not what the catalyst is. So the way to do this experiment then is to do it high enough flow so that the conversion is small, and so we know exactly what the concentration through the bed of the catalyst is. So then what can we do with this? So here are 3 samples. This is the chavazite structure on a SAPO, ZSM5, and the copper chavazite. So here's the Zane spectrum. I mentioned to you that there is a transition here that's very characteristic of copper 1. And plus also the shape of all these, the Zane curve is very important. If you have an interest, I can show you the different standards we have. Those lines will be quite different, and so this was all done under differential conditions. So we're measuring the kinetics at the same time that we are getting the SCR data. And so here are the results. The three samples I mentioned to you. And so with the Zanes now you can find out how much copper 0, copper 1, and copper 2 you have. The edge position also is important, but it's almost the same. So you can see here there's a huge variation, and you saw by the size of those lines. But now you compare with the rate. So here is the SCR rate. Just gave you the conversion, but the important number is here. So you can see, although those 2 catalysts here have very different copper 1 to copper 2, the rate is about the same. And then the ZSM5 has also a different number, but it doesn't correlate. So the amount of copper 1 or copper 2 that you have, it doesn't matter. So this is not, that's telling to us that's not the copper 1 or the copper 2. It's something else. Otherwise, there will be a correlation between maybe the copper 1 or the copper 2 and the rates. So then, again, to understand the complexity of all this, Bill Schneider has done some calculations. I showed you here one plot. There is a similar one that has water with NO2. So what he did is he studied the stability of different compounds, and the letter Z means that you have the zeolite, and on the x-axis on top, you see a measure of the oxidation strength of your mixture that looks at NO plus NO2 with oxygen. Depending on where you are there, you know how much oxidizing your medium is. And you can see here the compounds that are most stable, which is this on +2 would be that one, and +1 would be that compound. We can calculate the coordination number and the bond distance, and we can do the same thing using x-axis. So here, what happens on the fast SCR, you see the coordination number and the bond distance. If it is in the +2 state, and here is the, in this case here is mostly NO2. Because there is NO2, the copper is oxidized on the +2 state. On the standard SCR, we know that there is less, so that's, and if it would be completely +1, the coordination number would be 2, so it's a mix. So we measure the average under standard SCR. So you can see by x-axis that under standard SCR, you have mostly, in this particular catalyst, in this particular conditions, a +2 state, but they're very dependent on the reaction conditions. But with this technique, you can tell how much experimentally, and then we're comparing with Bill Schneider on finding out what kind of coordination number and distances you have. And here is some of the this compound here that I told you that is calculated. So, our idea of what's going on is we think that there is a copper 2 site that has this 4 coordination and a copper 1 that has a 2 coordination +1, and there is a redox cycle, that catalytic cycle that goes around between this compound and that compound, and so this cycle goes around. That's why when I showed you 3 different catalysts, the amount that you have under reaction condition depends on the reaction condition, depends on the zeolite. But there was no correlation because it depends. It will depend on this particular ratio, what's going on. So the experiments that we thought about doing is that we have an SCR reaction, 300 ppm of NO and ammonia and water and oxygen, and then at time 0 we can take either the NO or the ammonia or the oxygen out, and in each place we put CO2. And so the CO2, we're doing this by using an IR instrument. We can see the reaction hold up to see how much the gas it takes to wash the reactor. And at the same time, then we can see what happens with the rate and with Zangs at the same time. So then we can do a transient experiment to find out how the catalyst is going on. So here's one example of what you do with oxygen cut off. So there is a delay because until you get into the IR, you can see that the CO2 comes right up, and this is the hold up. The gases are flushed out pretty fast. And you can see here that the ammonia still takes a while to. There's still some reaction going on. That means there's still catalytic cycles going on after you take the oxygen out. So then this is done just to show you this is the Zangs part. We measure the Zangs at the same time that we're measuring the reactivity. Probably it's better to see the data in this case. So here is, we took that Zangs that I just showed to you and we deconvoluted that, and what happens with the isolated copper 1, the isolated copper 2, and then the hydrated copper 2. So those are the compounds that make up the Zangs. And so here in this graph, you see the normalized rate of consumption, including the isolated copper 2 to isolated copper 1 as a function of time. So here you can see what happens in the gas phase and what happens with the catalyst. you can see that there is a very good correlation between the ratio, the catalyst going from copper 1 to copper 2 to copper 1, and the rate. You can do the same thing with NO cutoff experiments. And so here is, in this case, you cut off the NO. You can see the CO2 comes up, then the NO comes down. You cross at about 0.5, and then you can still see a little bit of a reaction going on, but you see that the reaction ceases very fast. So this is the other side. So we took the oxygen out. Now you're taking the NO side. So this is on the reduction side. So then what happens here then is that with the NO cut off, then the copper 1 oxidizes to copper 2, and copper 2 signature is that you lose this peak here. And then you see those, and you see here cut out what happens with the catalyst. So again, if you look at what happens as a function of time with all the coppers, so under standard SCR you have about 70% copper 2 and 30% copper 1, and when you make the switch as a function of time, it very quickly goes into a new state. And if you want to follow this, look at what happens with the reaction. So here you see the tracer, and the NO, the reactivity comes down very, very fast. And then this is what happens with the oxidations, the ratio of copper 1 to copper 2. So then with the cutoff experiments, we can isolate the reduction portion of this reaction. Of course, we see a large increase in isolated copper 1, and that follows what you see with the reactivity. If we cut off the NO, then we isolate the oxidized portion, and then the catalyst gets fully oxidized to copper 2. And so, and also you saw on the transient response that there is a correspondence between the ratio of copper 1 to copper 2 and what the reaction of O2. I didn't show that to you, but those experiments are reversible. So if you bring back the O2 or the NO, then the catalyst returns to this ratio of mixed oxidation state under reaction condition. So then the question is, what would be the state of the copper under reaction condition? So that's a question that the x-axis is not going to tell you exactly what those are. I showed to you that if the catalyst, before it goes into the reaction media, the copper is swimming everywhere. So it looks like this hexa copper compound, but under reaction conditions, those bonds break and you start forming bonds with the catalyst. Bill Schneider, from his calculations, I showed to you that this is what he thinks will be the most stable, at least copper 2 and copper 1. But of course, this is a function of reaction conditions, and also we calculated for SSD 13. So in conclusions, I showed to you that NO oxidation alone is not a good metric. It's very good way of characterizing the catalyst. You can find out how many types of dimers you have. The standard SCR itself you can use to find out how many copper 2+ you have isolated. So and we know, I think we have, we think that the reaction goes on copper dimers for NO oxidation. And for SSD13, the SSD13 is the active sites, and there is the active site is it's a redox site. So with that, I would like to thank you, some of our students and funding sources, some funding from governments and Department of Energy, and thank you for your attention. I'll be happy to answer.
We have plenty of time for questions. Chuck Dean again. I have really more of a comment than a question, and that is I completely agree that in general operando experiments are going to be better than in situ ones. But you have an additional problem with this system, and that is that at least in our opinion, and we recently published on this, even under low conversions, the rates are limited. They're affected by mass transport, internal mass transport within the zeolite, because the zeolite pores are so small. And so if you make a rate measurement, the turnover frequency is what you want. The turnover frequency is really meaningless if you're not accessing different portions of within the zeolite.
Oh, absolutely.
And so if you, for example, if you try to say that, and you have an additional problem with, if you're trying to say a spectroscopic measurement of the copper and trying to correlate that with reactivity, because say it's a ratio of copper 1 to copper 2, for example, and you don't access much into the zeolite, yet you have a bunch of copper there. You've got this bath of copper 2 that's never even seen in the reactor. So it's an artifactual measurement.
Yeah, no, I agree completely. So if they're going to do catalysis without showing first that there is no heat and mass transfer, so we cannot go to maybe the temperatures that would be sometimes relevant. You can go to 400 degrees C. We can't go to those high temperatures. So at those conditions, you're right, we cannot probe what it is, but we think that the lower temperatures we can. But as you go to higher temperatures, yeah, you're right, we cannot. And then there may be all kinds of problems, like say core shell type of model, you have something on the surface and on the bulk. You know. But we think at our conditions, we think that we don't have a mass transfer. And one good proof of that, in fact, it's called a Koros-Nowak test. What you can do to prove exactly that, you take a catalyst and you change the number of active sites. If the rate is proportional to the number of sites you're putting in, that means there's no mass transfer limitations. And that's the graph I showed you in the beginning, that there's a perfect correlation between the amount of copper and the rate. So that is what's used to show there's no mass transfer limitation. But that's at about 200 degrees C. At 400, I can't do that. So maybe just I'm not sure if you agree, but what we think is going on is that at our conditions, I don't think we have mass transfer, but at higher temperatures, I think yeah, people get into trouble.
Thanks for the nice one. Santosh from Swiss Federal for Material Science and Technology. I have been attending all these talks, copper sometimes. Maybe I'm wrong, but I have been seeing that only isolated and dimers are the species which are formed in the zeolite. But we have also seen a talk from Alex group where they have seen after hydrothermal aging, they saw the increase in the total acid. Did you see any, besides these two species, did you see any other copper species, like nanocopper forms? If you have seen, what is the role of those species in that? This would be one doubt. I thought you would be the right person to answer. The second one would be the why chalcocite is so hydrothermally stable, because zeolites, all of them are aluminosilicate or silicate. What makes the chalcocite so special?
Oh, that one I answered already. I said ask Carolo. So for the second one, I don't know why makes them so stable. It is amazing, but I don't know. For the first one, so what we are doing is our work is more academic, right? So we add certain amounts of copper in a very deliberate fashion, so we don't overload. So for example, we probably well, I told you the theoretical limit here is about 0.2, and then after that, there are no at least no more sites to put the copper. Then after that, the copper, if he wants to be there, it has to be in a different form, and we think it goes into diamond. And if you keep on loading copper, I think you'll go from diamonds to something else. So eventually, if you put enough copper, they will go outside of the, even outside of the cage, and you have clusters there, and they'll do probably different types of chemistry, probably oxidation of ammonia and so on. But so in our case, we've seen only those 3 species because of the loading. We keep the loading relatively low. So that's what we see. Yeah, it is asking the copper sites are mobile, and that's what you see. In fact, if you leave them in air, they swim on the zeolite. We know that they go all over. But under reaction conditions, then they grab those aluminum sites and they stay there. If you are below in this particular silica to aluminum ratio of 0.2, I think that they are quite stable.
Got time for one more question?
So what happens to the annual oxidation if you add water to the reactant?
So if you add water, the rate goes down by about 2 orders of magnitude.
Even at the very low copper load.
Yeah. So on the data that I showed here to you is if you add the water too, even small amounts of water, it's not a linear effect. Even small amounts of water, the rate goes precipitously down. Because probably the water competes with something there. We don't know exactly what, but even small amounts of water, 0.5%, for example, you lose most of the rate. Then from 0.5%, maybe we did to 5%, you lose another now 30%. Most it's probably very strong absorption of water on this, of course, which is temperature dependent, right? So your question is what happens at the temperatures that we try, huge inhibition, but at higher temperatures, I'm sure it's less than that.
Let's thank Fabio one more time.